constructed, it's time to follow Apollonius in cutting the cones in different ways to reveal the several conic sections. So the first, we're going to get our knife.
What?
And
No.
We're going to take our knife, and we're going to start off with the most trivial of the conic sections, that of the axial triangle. If you take your cutting plane and you drop it through the vertex, you're going to get, let's hope this doesn't destroy it, but it did. We're going to pretend it didn't do that. For TV. And then you pull apart the parts, and you have an axial triangle. The axial triangle, as he talks about, is the section that you get anytime you drop a cutting plane through the vertex of the cone. And like I said, this is the most boring version, or the most boring of the sections. So let's get to something more interesting. It's okay, we can just keep running and cut stuff out. Alright. Now that we've covered the most boring section, that of the axial triangle, we're going to do the second most boring, and that of the circle. If we have a cutting plane that is parallel to the base of our cone, we should get a circle. And lo and behold, we do. So the triangle and the circle are both conic sections. We can probably stop. So that I'm going to reform the cone. These next sections are a little bit more delicate. So now that we've done the axial triangle and the circle by cutting the cone horizontal to the base, what if we were to take that cutting plane and just kilt it a little bit? If we take it and kilt it so it's not parallel to the base, but it's still going to cut through the whole conic surface, this is the shape we get. It's not quite a circle. It looks like a circle that's squished a little bit. All right. Now, what if we were to take that same cutting plane and we're going to kilt it and keep on turning it until it is parallel with the opposite side of that cone? We would get a cut kind of like this. Ooh, that is dangerous. Ooh, didn't even go all the way through. But you can see here that we get this U-curve, right? And this will never close. Because it's parallel to the opposite side of the cone, that cutting plane will cut and cut and cut and go on forever and will never finish cutting through the cone. So this is an infinite curve that is kind of like a U. The last conic section is going to require a different model, so we're going to have to stop here. So what I had been using in the previous sections was technically just a cone, just one part of the conic surface. But if you remember how Apollonius defines the generation of a conic surface, namely that there's a circle in a plane, a point not in a plane, and the line going from that point to the circumference of the circle, and then going around it in space. But that line goes infinitely in both directions. So while that would generate this cone here, it would also create an identical cone up above, like this. So, we've talked about the different cutting planes. If we go through the axis, or through the vertex, that fixed point that we use to generate the conic surface, we're going to get a triangle. If we cut parallel to the base, we're going to get a circle. Kilt it a little bit, we get kind of like stretched out circle. Keep kilting it until it's parallel to the side of the cone. We're going to get an infinite curve. But what if we bend it or tilt it just a little bit more? And for the purpose of this demonstration, I'm going to kilt it a lot so that it's essentially vertical but not going through the vertex. If I kilt the cutting plane all the way here, it is definitely going to cut this plane, or this cone, I should say. This is going to be difficult. So it's definitely going to cut this cone down here. But again, this cutting plane is going infinite in both directions. Ooh, how am I going to do this? So it's also going to cut this cone up here. There. So now, if our cutting plane is not parallel to the side of the cone, then it's going to cut the entire conic surface, once down here and once up here. So that one cone cut generates these two curves. They look similar to the other curves, or the one that we saw before. They are both going to be infinite, but what's different is that we have two curves. One cut gets us one curve. Now, if you're thinking, why didn't the previous one get us two curves as well? Remember that the cut was parallel to the side of the cone. So if it's going to be parallel to the side of the cone, it's also going to be parallel to this side of the cone as well. So it'll never cut that top part of the conic surface. All right, so let's review in a minute. So, to review, we have our primary conic sections. The first one we looked at was when the axial triangle, but we're going to skip that. If the cutting plane is parallel to the base of the cone, we get a circle. It's a little lopsided, but whatever. And you'll notice that there's exactly one angle at which the cutting plane can come in to cut off a perfect circle, namely when it's parallel to the base. The next section, if we take that cutting plane and we kilt it a little bit, then we get this curve. It's kind of like an elongated circle, and it is called an ellipse. You'll notice that that there are infinitely many angles that we could cut the cone at to generate an ellipse. From when it's parallel to the base to our next section when it's parallel to the side of the cone. That's when we get this single curve that goes on forever, and it is only one in number. This curve is called the parabola, coming from the Greek meaning to throw alongside. It is thrown along, the cutting plane is thrown alongside the side of the cone, and so generates that one curve. And between the cut of the circle and the cut of the parabola, we get all kinds of cuts to generate these elongated circles, these ellipses. But if we can throw alongside the cone, then we can also throw beyond the side of the cone. Namely, if we continue to turn our cutting plane, we can generate this last conic section, which consists of two curves, one in the lower part of the conic surface and one in the upper. And this is called a hyperbola. A hyperbola is made up of two curves opening in opposite directions, and comes from the Greek meaning to throw beyond. All of these conic sections show up everywhere in the created world. And even though they were just the musings or experimentations of some guy thousands of years ago, they still have remarkable implications for us today and really shape how we see the world around us. This idea of different sections of a object might be a little bit familiar to when we were talking about the fourth dimension. That if you lived in a flat world like the surface of this table, and you wanted to explain what a cube was to someone who lived in that world, some ways that you could do it is that you could drop, say, a cube through their world and think about what they would see. At first they would see a point, and then they might see a triangle, then a quadrilateral, then maybe even a hexagon. Those are all different sections. It's kind of the way an MRI machine works. You're seeing different slices of it at a time, and that's exactly what we're doing with these conic sections. But before we continue with the conic sections, think about some other mathematical shapes. If we take a sphere, it's not very interesting with regard to conic sections, because pretty much any way you slice it, you're just going to get a circle. But if we take something like a cube, we can get a lot of diversity. We can get a square if we cut it parallel to the sides of it. If we tilt it a little bit, we could even get a six-sided shape, a hexagon. We could cut it such that we just cut off a little corner and we end up with a triangular section. So think about the different ways that you can cut a cube to get different sections. If we take a torus, which is like a donut, remember this is the kind of world that Pac-Man lives on, Mrs. Pac-Man. There are all kinds of different sections that you can get. You can make one cut and get two circles, for instance. You can cut it kind of slanted, and you get this elongated circle. The question might arise, is this the same kind of stretched circle that we saw when we cut the cone? These are good questions to ask. If you take a tetrahedron, that is a four-sided solid, there are all kinds of ways that you can cut this. Obviously, you can just cut it parallel to the base and get a simple triangle. You can just kind of cut it vertically, and you cut it perfectly vertically, we should get something like an isosceles triangle. But we can also cut it in such a way that we can get a quadrilateral. That was not a good example. But there are different ways that we can cut a tetrahedron and get shapes that have more sides than a triangle. Lastly, we can take a cylinder. We can cut in all kinds of ways. If we cut it, just straight through the top, we're going to get a rectangle. That probably makes sense. If we cut it horizontally, we're going to get a circle. But what if we cut it slanted as well? We know that cutting it parallel to the base will get us a circle. But if we cut it kind of diagonally, again, we get this stretched circle. Is this an ellipse, like we saw with the cone? And is this an ellipse from cutting a torus? These are all the kinds of things that we want to start thinking about. Thinking about different things, even in your own house, that if you were to cut it, what kind of shape can you get? How many shapes can you get from cutting up different things?